In this example, let's solve a current carrying wire. And we're going to do it two ways. We're going to, first of all, do it with the Biosevere Law. But then afterwards, we're also going to use Ampere's circuit law. And we'll see that one is much easier to do than the other. So for comparison purposes, recall that in the electric field, we also have a similar example where for a charge, you can solve it using, and you're trying to find the electric field. You can either use Coulomb's law or that formulation to arrive at the electric field, or you can use Gauss's law in integral form. And in our highly symmetric example, we see that Gauss's law in integral form was much simpler. In this situation, we'll also be following kind of the same playbook and telling a similar story. So we'll start by using Biosevere Law. I'll derive what the solution looks like, but then we're going to see that Ampere's circuit law in integral form works much better in this highly symmetric problem, and hopefully you'll become fans of Ampere. Let's start by setting the problem up. We have a current carrying wire in the z direction. So we'll define this as x, y, z. The current will be running along here. It's an infinitely thin wire running, again, in the z direction. And we're going to solve it two ways. Let's start with the Biosevere Law. So for the Biosevere Law, what we're going to do is we have our current segment, dl cross r, divided by 4 pi r squared. If we take the integral of that, so add up all the individual line segments from minus infinity to infinity, since it's an infinite current line, that will give us the electric field, the magnetic field. In contrast, Ampere's law, we're going to use the fact that the closed loop integral of h dl is going to give you the current enclosed to find the solution. Well, let's start with the Biosevere law. So in many of these situations, the main trick is to define all of these individual elements. Namely, the source observer vector is an area where you can never get enough practice. So let's start by defining that. Let's say your observer is over here, and this will be in cylindrical coordinates. What would this be? This would be rho. And then let's say we're arbitrarily looking at a current element up here at coordinate z, and remember the prime refers to the fact that it's a source vector, right? So remember the source observer vector is r minus r prime, where r prime is the source. So the source observer vector is this vector over here, r. So once we've written it out like this, you can start defining it. This short segment, dl, is going to be in the dz direction. And now we just have to plug it in and solve for it. So our dl prime is going to be equal to dz prime in the z hat direction. So our short length segment is z, and then the unit vector is in the z direction. And our source observer vector is going to be r, which is going to be rho hat, minus z prime z hat. R is rho hat, and r prime is z prime z hat. Now you might ask, how do I know that this is at the origin? The answer is, remember, this is an infinitely long wire, and it's the only thing in the universe. You're living a very sheltered life right now. And so we're going to use symmetry. right? If you stand up here and you look up and you look down, you're going to see the same thing as if you're standing at z equals 0 and looking up and looking down. Either way, you just see infinite current going up and infinite current going down. And so it doesn't really matter where you put it, so you might as well put it at the origin and make your life easier. So now we have r. In many cases, remember, if you want, we also need the unit vector. Actually, in this equation, I misspoke. This is supposed to be little lowercase r, but if you wanted to just make it in terms of uppercase R, you would have to write it as uppercase R divided by its length, right? So if I already did that here, where I have this uppercase R, this lower R squared should be R to the third, because this R gives an extra factor in, just to make life a little bit confusing because I forgot something. But now that we have R, we can also find the length R, which is going to be Pythagorean theorem. Works nicely here, so it will simply be rho squared plus z prime squared to the 1/2. And now let's also do this cross product so that we can eliminate as much of the vector calculus as we can before we start diving into ugly math. So dl cross r, remember I is just a scalar, so you don't have to worry about it for the purposes of calculating vector quantities. So let's plug in our dl, which is dz prime z hat, cross our r, which is rho hat, plus z prime z hat. Now remember, the cross product is 0 if they're in the same direction, right? So in this case, z cross z is going to be 0, so you don't have to worry about this term. Yay, finally something works out well something works in our favor. So if we take this cross product, we have rho dz prime, and then what direction is this going to be? Z cross rho, which again, the way I like to remember this is I just go rho phi z, rho phi z. If I'm going this way, I just keep looping it. If I go to the right, I don't have to add a negative sign. If I'm going to the left to get what I want, then I do need to add a negative sign. So z cross rho is going to just be equal to positive phi. So now we plug that into our expression for h, plug all these quantities in, and then all you are left with is just a very ugly integral. So we're going to plug this in, and we're going to get 1 over 4 pi, and then integral from z prime equals minus infinity to z prime equals infinity. I'm going to get I rho dz prime all over rho squared plus z prime squared to the 1/2. And let's pull all the constants out. So we're going to be left with I rho in the phi, oops, I forgot the unit vector here, in the phi direction over 4 pi. And then now you are left with this one integral going from minus infinity to infinity of dz prime over square root rho squared plus z prime squared 1/2. And you look at this and say, what am I going to do? Well, this is where you have to stand on the shoulders of giants and either go to your favorite online resource, or if you're really old school. Back in my day, we had these books filled with integrals called an integral table. And back then, one of the ways that you could do, if you wanted to really show your street cred, is to have that book sitting on your shelf. Pull that book off your shelf with a thoughtful look, scroll desperately through the pages, flipping until you see something that looks similar, and you will find in this integral table that minus infinity to infinity dz prime of square root rho squared plus z prime squared to the 1/2. Speaking of errors, one thing that I messed up with, this is not the square root. This is r, but remember this is r to the third, so this should be to the third 3/2 power. So now you're going to look at the integral for dz prime over rho squared plus z squared to the 3/2 power. that is going to be equal to z prime over rho squared plus z prime squared to the 1/2. And I don't know what brilliant grad student figured this out to make that table into the contribution as their contribution, but they are immortalized for as far as I'm concerned in this problem. So this integral, again, dz prime over rho squared plus z squared to the 3/2 is going to be equal to z prime rho squared plus z prime squared to the 1/2. And then we're going to evaluate this from minus infinity to infinity. After all that work, you are going to get a very anticlimactic 2 over rho squared. So now we're just plug that in here, and then we will get our final answer, which is that h is going to be equal to I rho over 4 pi, and then plug the integral in, 2 over rho squared in the phi direction, and you get that h is going to be equal to the lovely expression that we saw before of I over 2 pi rho in the phi direction. It's a lot of ugly math involving barrier here that required us to either to pull an integral table off our bookshelf or pull out a computer, but in the end you get this nice little expression that we had talked about before and are somewhat familiar with.